proportion. So suppose we wanted to determine the number of households in Monroe City that would favor a tax increase to fund a new baseball field. I guess this question was more relevant last year or the year before than it is now. But ideally, we would ask all households to find a proportion, but that's often not possible. Okay, if I wanted to know if people are going to support it, I would go talk to everyone, and then I would know for sure. But is it feasible to think that I would go visit every single house in Monroe City? Probably not. I could, but then if I went to Hannibal or Columbia, it would get even harder as the number of people got larger, okay? So it's just not feasible to assume you would talk to everyone. So instead we can find what's called a point estimate, right? It's kind of similar to what we were doing with the sample means. We basically, when we were trying to find that, we were looking at taking a sample and getting the mean of those. Except this is a scenario when we're really not worried about the mean. It's like a yes or no. Do you favor this or do you not? And I can get a sample of people and figure out what proportion of those would be in favor. So your proportion, we call it p hat because it's representing the sample. It's just x over n. X being the number of people in my sample that said yes, n being the total number in my sample. Okay, so ideally, I would use that to estimate the whole group. So if I went and talked to 100 people in Monroe City and 75 said yes, what would my p hat be? 75 over 100, so 0.75. So from that, I might estimate that 75% of all the people in Monroe City would be in favor. Okay. So you guys look at this one. Take a second on your own, read the question, and answer it for us. So we had 1,745 registered voters were asked if they approved the way the economy was handled. 349 said yes. So the point estimate, p hat, x over n, so that would be 349 over 1745, which gives us what? 0.2. Everybody got that? So pretty easy to find the point estimate. Now, just like it's easy to find the sample means, what we start doing is taking like all the possible samples and getting all the possible means, and that created the distribution for the sample means. So we can do the same thing with these proportions. Some of the key points, we know, just like we saw with the means, the bigger our sample, the more normal it will become. So for a small group of n, it's probably not going to look normal, but as n increases, it will become more normal. The mean is the population proportion. Okay, that's different than p hat. P hat is for my sample, but the mean of the distribution of p hats would be the same as the true population proportion. The standard deviation will get smaller as my sample increases, just like we saw with our sample means. The more you include, the less error there is in that. So this is kind of our key slide. So our distribution for the p hats. Yesterday with sample means, we said either the original data had to be normal or what had to be true about n. I'm actually cold. It had to be bigger than 30. So if either we had to know it was normal or if we had to have more than 30, with p hat, it's different criteria. We can assume it's normal if n times p times 1 minus p is greater than or equal to 10. That is something that's not on the formula sheet. All of our means and standard deviations are, but the criteria are not. So that's going to be the big difference between when we're talking about the x bars versus the p hat. X bar, either normal or more than 30. P hat, n times p times 1 minus p greater than 10. The mean of the distribution of p hats is p. That's on our formula sheet, and standard deviation is also on the formula sheet. It's the square root of p times 1 minus p over n. There is one other criteria. For this to be true, for us to be able to look at it, all of my data has to be independent. Do you remember what independent meant? They don't affect each other. In general, we can assume it's independent as long as our population is big enough. So if our sample is less than 5% of the total population, we can assume it's independent. Right, so that is another little criteria that we need. Either I have to tell you it's independent, or the sample has to be smaller than 5% of the whole population. Right. The mean and standard deviation piece, that doesn't change if we don't have a big enough sample to assume it's normal. It's just that we would no longer be able to look up probabilities on the normal table if it wasn't normal. So let's do some problems. So according to a poll, 42% of registered voters believe the president should be impeached. Describe the sampling distribution of the sample proportion. So when I ask you to describe it, I'm asking you to check the criteria and tell me the mean and the standard deviation, just like we did yesterday with the X bars. Criteria. We actually have two that we have to check here. The first one, because did I tell you anywhere that it was independent? No. So we need the sample to be less than 5% of the total population. If I gave you the population size and the sample size, you could confirm it. A lot of times I won't, but if I'm talking about 10 people, would that be less than 5% of all registered voters? Absolutely. Even 100, is that less than 5% of all registered voters? Yes. So a lot of times there's not much calculation to do there, it's just kind of acknowledging that we thought about it. If we're talking about the whole United States, all the voters, there's a lot of those. The second one, did I tell you that it was normal? No. So we need to check the n times p times 1 minus p is greater than or equal to 10. Did on yours, did I just have for n equals 50? I thought I changed that. I didn't change it on this one. Sorry. We're just going to stick with 50 and do it one time. So if I do that, my n, what's my p? 0.42, because that was talking about all the registered voters that we were looking at, and 1 minus 0.42. That gives me 12.18. So that's bigger than 10, so that means it is approximately normal. Maybe not perfect, but close enough. So now, the mean. The mean for the p-hats is the same as the population proportion, which is the p, 0.42. Standard deviation is the square root of p times 1 minus p divided by n, and we were looking at 50. And we get 0.0698. So this was all I asked for on the problem, describing the sampling distribution, criteria, mean, standard deviation. But if I asked you to find any probabilities, what do you think we would do at this point? Turn it into a z-score, use the table, just like we have it. The only difference is, when your variable is p-hat, you have to have the mean and standard deviation for p-hat to do that. So let's try one of those. I think after most of these, I included a blank slide, so you would have a little extra space to write, just since we have a few more criteria to check. So according to the Centers for Disease Control and Prevention, 18.8% of school-age children ages 6 to 11 were overweight in 2004. In a random sample of 90 school-age children, 6 to 11 years, what is the probability that at least 19% are overweight? Before I can do anything, what do I need to do? We have to check the criteria. All right, and so that would be worth points. Test or quiz, you have to show me that you're checking it. Okay, first criteria, I never said it was independent, so we need to know that our sample is less than 5% of the total population. Again, I didn't tell you the entire population size, but if we're talking about all 6 to 11-year-olds in the United States, would 90 be less than 5%? Yes, absolutely. Second one, we need to check the n times p times 1 minus p is greater than or equal to 10. So my n is 90. My p, that is the population p. So what was that? So we'll use it as 0.188. Okay, that is probably the biggest thing. This 19% is talking about my sample. That's a p hat. So we're looking back there at our p. 1 minus p. So we get about 13.74, bigger than 10, so that criteria is met. So that means we can keep doing this problem. All right, we want to find the probability that at least 19%. So it's a percent, that's like a proportion. We want at least, so that means what? Greater than or equal to 0.19. Alright, if I'm going to turn that into a z, we have to have the mean and standard deviation for p hat. So the mean is my population proportion, my p, which was standard deviation is the square root of p times 1 minus p over n, which was 90. Keep a few decimal places on this. So 0.0412. So now we can get our z, which is our value minus the mean divided by the standard deviation. These we only need 2 decimal places. So we get 0.05. So we have to find the probability that z is greater than or equal to 0.05. How do we find greater than from this? 1 minus. So we look up 0.05 and we get 0.5199. So that is 0.4801. Any questions there? So part B, suppose that a random sample results in 24 overweight children. What might you conclude? All right, I'm still talking about a sample of 90. So I still have the same mean and standard deviation. But this time, if I tell you 24 children, we have a mean and standard deviation for p hat. How do I get a p hat from that? So my number of children, which is 24, divided by the number in my sample. So my p hat is 0.2667. So I didn't have to do that on part A because I gave you a percent. Anytime I'm giving you a percent, that's a p value. But this time I told you the number of children in my sample, so we had to first find that p hat. All right, so I'm trying to decide if there would be anything strange about this. Is that higher or lower than we would expect? What was our mean? 0.188. So this is definitely higher. So I need to find a probability. Just like we did one yesterday, we don't have the option of finding an equal to. So should I find greater than or less than? Greater than. I expect it to be less than. So if I find the probability being less than that, that's not really telling me anything because the mean is below that. But let's find the probability being greater than this. So we need our z. So our value minus the mean divided by standard deviation. We need to find probability being greater than 1.91. Greater than means 1 minus. .9719, which gives me 0.0281. All right, what's that tell me? This is unusual. Okay, so what kind of conclusion can we make? This is very unusual. So what do you think that means? What does that tell us about our sample? It probably wasn't very good, or for some reason that sample is different than the rest of the group. So we don't really know exactly what this means, but a couple possibilities. Either we have a bad sample for some reason, or the sample is different. Maybe it's not necessarily a bad sample, but something is causing that group to be different than the whole population. Or the real mean has changed and it's really gone up. So it's kind of a red flag. We would have to do more investigation to figure out what the actual cause is. But something along those lines. So any of those answers would be okay. I said, what might we conclude? So the sample is different in some way. Might be one option. Or you could say it was a poor sample, or you could say the real mean may have changed. Any of those things are fine. And if we were trying to figure out what was going on, we would probably start by taking a closer look at our sample and seeing, do we have any bias? Did we pick children all from one school? Maybe that school is different in some way because of ethnic groups or lunch choices or something along those lines. Let's take a look at another one. According to the National Center for Health Statistics, 15% of all Americans have hearing trouble. Part A. In a random sample of 120 Americans, what's the probability that at most 12% have hearing trouble? So first, what do we have to do? Okay. First, I never said independent, so we know the sample has to be less than 5% of the total population. Would 120 Americans be less than 5% of all Americans? Yes. Right, second one, n times p times 1 minus p greater than or equal to 10. And that's 120. What is the p? Careful. It's 0.15. The p has to be for the whole population. So that was looking at the survey they had for all Americans.
Did you say the trigger here is just completion? Yeah. Do you want me to write it if they got it wrong and mark it?
You don't even have to do that. You just want to tell me if they did it. All right, and so that's greater than 10, so we're good. We can move forward. So part A, we want to find the probability that at most 12%. So we're finding the probability, it's a percent, so it's a p hat. At most means what? It can't, at most can't be any more, so less than or equal to. So we need a z, which means we first have to get the mean and standard deviation. The mean for p hat, that is the p for the whole population, which was 0.15. Standard deviation is the square root of p times 1 minus p divided by n, which was 120. And we get 0.0326. So now we need a z. Z is our value, which was 0.12, minus the mean, 0.15, divided by the standard deviation. Again, negative 0.92. So we're finding the probability that z is less than negative 0.92. Less than is what our table gives us. So that is 0.178. Part B. Suppose that a random sample of 120 Americans who regularly listen to music using headphones results in 26 having hearing trouble. What might you conclude? So what do I need to find first? So p hat, x over n, so 26 over 120, which gives us 0.2167. Alright, so we have our p hat. And is that higher or lower than my original mean? Higher. So to figure out if this is strange or not, we should find the probability that we are more than that. If it was less than average, then we would find the probability of being less than, right? Because we would expect it to be more. Okay, so now we need to get a z. So our value minus the mean divided by standard deviation gives me a 2.05. So we'll find the probability that Z is greater than or equal to 2.05. Just a side note, on this one, if you had rounded your p-hat to 3 decimal places, your Z would have turned out to be 2.06. So it's just very important to show me all of your numbers so I know where they're coming from. Okay, don't just try to give me a final probability. Then I don't know if the difference is due to keeping one less or one more decimal place or not. So greater than is 1 minus. We look up 2.05. And we get all right, so is that unusual? This time I did give you a little bit more information about my sample. Those particular people were ones who regularly listen to music using headphones. So what kind of conclusion could we draw? Okay, those who use headphones have more hearing loss. Do you guys have any questions for me? Really, the hardest part about this is remembering the criteria and being able to tell, okay, am I checking for X bar or p hat? After that, they're pretty much the same. You use your formula for mean and standard deviation, get a Z, and look up your probability. So after that, they're all pretty similar. So you guys have a lot of time now to work on that